Today I'll discuss point symmetry groups, which are also briefly called point groups. Let us start with an example. Consider molecules like chloroform or ammonia with a lone pair of electrons, etc. Such molecules have a structure whose skeleton is like this. There is a threefold rotation axis, C3, and three reflection planes, sigma V1, sigma V2, and sigma V3. The symmetry elements are collected here. Identity, C3 axis, sigma V1 plane, sigma V2, and sigma V3. Using these symmetry elements, we can have a collection of symmetry operators. They are identity operator, C3 operator, C3 square operator, reflection operators like sigma V1, sigma V2, and sigma V3. Let us call this whole set of symmetry operators S. We also define a composition rule, that is a rule for combining any two elements of this set. The rule is this: Ri, Rj. This is a rule for, this is a symbol for that combination rule. Ri, Rj means successive rotation of these two operations with Rj first and then Ri. Sometimes this symbol will be omitted for convenience. This will simply be written as Ri, Rj. This will be operated first, then Ri. This is the composition rule. Now, using such a combination rule, that is symmetry multiplication, one can construct a symmetry multiplication table. I discussed construction of such tables in one of my earlier videos. The link is given in the description box. You may find it there, the construction of this table. Now, these are the symmetry operators in that set S. These will be considered as the first operation, and the same operators are also written along this column. These will be considered as the second operation. The body of this table is obtained by carrying out actual symmetry multiplication. For example, C3 square followed by C3 will give you E. Sigma V1 followed by C3 will give you sigma V3, and so on. Now, we can utilize this table to examine some interesting properties of the set S. The first is closure. Let us take any two members of S, say sigma V2 and sigma V3. If we combine them, that is multiply them, then sigma V2 first followed by C3 will give sigma V1 from this table. Sigma V2 first followed by C3 will give sigma V1. And this operator also belongs to the set S. These two belong to S, and their product, sigma V1, also belongs to S. Similarly, sigma V1, sigma V2. Sigma V2 first, then sigma V1 will give you C3. This C3 also belongs to S. Therefore, product of any two symmetry operators is also a symmetry operator which belongs to the set S. So, the set is closed. Closure property holds for the set S. Written simply, for any Ri and Rj in S, Ri Rj belongs to S. This symbol stands for belongs to. This symbol stands for belongs to. The next interesting property is the existence of an unique identity element for the set S. The unique identity element is E. Consider this table here again. E followed by C3 gives C3. E followed by C3 square gives C3 square, and so on. When the first operation is E and the second operation is any of these, the result is the same operator back. So E acts as the identity operator. Similarly, if you take E as the second operator, then C3 followed by E is C3, C3 square followed by E is C3 square, and so on. So this identity operator, this E operator acts as the identity operator in the set. And this is the only one and only one operator which acts as identity. C3 or C3 square do not act as identity, because C3 combined with any other element will give another element. Identity operator in this set is unique. One and only one such operator exists in S. So unique identity exists. This is the second important property of S. The next is existence of unique inverse. For example, C3 multiplied by C3 square gives you identity. The reverse, C3 square multiplied by C3 also gives identity. So C3 is the inverse of C3 square, and C3 square is the inverse of C3. Similarly, every element has its own inverse in this set. This is the third interesting property of the set S. And next, we have to examine associativity. We have to examine associativity. Consider any three elements, say sigma v2, sigma v1, and sigma v3 from the set S. We have taken these three operators. Now we combine these two first and combine this result with sigma v2. What is the result of sigma v1 preceded by C3? C3 followed by sigma v1, C3 followed by sigma v1 will give you C3 followed by sigma v1 will give you sigma v2. So this part is sigma v2, and therefore this whole part is sigma v2 combined with sigma v2, which is identity. And this exists, this belongs to S. We take the same three elements in the same sequence, sigma v2, sigma v1, sigma C3. In the same sequence, we take the same three operators, but we now combine them in a different way. We combine these two first and combine the result with C3. Sigma v2 followed by sigma v1 will give what? Sigma v1 first, then sigma v2 gives you C3 square. So this result is C3 square, and this C3 is left. C3 square combined with C3 will give you E. We thus see that these two results are the same. Therefore, at least these three elements are associative with respect to the symmetry multiplication rule. Similarly, if we take sigma v1, sigma v2, sigma v3, combine these two first and then the result with sigma v1. The result is this. Sigma v2 followed by sigma v3 is sigma v2 followed by sigma v3 followed by sigma v2. Sigma v3 followed by sigma v2 is c3. Sigma v3 followed by sigma v2 is c3, and c3 followed by sigma v1 is sigma v2. That can be obtained from that table. The same, if we now change the order of grouping, if we carry out such a multiplication in a different order, associating these two first and then sigma v3, and find out results from that table, we'll find that the final result is the same, sigma v2. These two results are the same. Therefore we can say that associativity holds good in the set of operators S. Therefore, all the four group properties are satisfied by the set of symmetry operators S. Hence, this set, together with the binary composition rule, this is a group, mathematical group. Such a group is called a point symmetry group because these operators themselves are point symmetry operators. Why? Because these operators keep at least one point of the object unchanged, unmoved. For example, this C3 axis keeps all the points on this line unmoved by a C3 rotation. Similarly, the sigma v1 plane keeps all the points on this line unmoved. Sigma v2 keeps all points on this line unmoved. So this central point remains unmoved by all the symmetry operators in this collection. Therefore, these are point symmetry operations, and their collection, because they satisfy the group properties, will be called a point symmetry group or simply a point group. All molecules or all ions having many atoms with a definite structure have their own point groups. Molecules are actually classified according to their point groups, and that will be discussed. How to determine point group of a molecule will be discussed in a next video. Thank you very much for your patience.